For part A, we use the fact that the speed of light is the wavelength of the wave times the frequency. So the frequency is c over lambda, or 3.00 times 10 to the 8th meters per second over lambda, which is 800 nanometers. And this gives us a frequency of 3.75 times 10 to the 14th hertz. In part B, we start by calculating the energy, which is the Planck constant times the frequency, or 6.626 times 10 to the negative 34 joules second times the frequency, which is 3.75 times 10 to the 14th per second, which gives us an energy of 2.48 times 10 to the negative 19 joule. And if we want to find the uncertainty of the energy, we use the fact that the change in time or the uncertainty in time times the uncertainty of the energy equals h bar over 2. And so delta E is going to equal h bar over 2 delta t. And we know that the pulse duration is 4 times 10 to the negative 15 seconds. So h bar, if we remember, is 1.055 times 10 to the negative 34 joules second over 2 times 4 times 10 to the negative 15th second, which gives us an uncertainty in energy of 1.32 times 10 to the negative 20 joule, and this is approximately 5.3% of the energy of the photon. So the energy is given, the energy of a given photon is uncertain by at least 5.3%. In part C, if F equals E over H, right, because the energy is FH, then we can say that delta F equals delta E over H, or 1.32 times 10 to the negative 20 joules over the Planck constant 6.626 times 10 to the negative 34 joules second, which is 1.99 times 10 to the 13th hertz. This is also about 5.3% of the frequency we found. In part D, the spatial length, delta x of the pulse, is the same as the distance that the front of the pulse travels during the pulse duration. So delta x equals c delta t, which is 3 times 10 to the 10th meters per second, times delta t, which is 4 times 10 to the negative 15th second, or 1.2 times 10 to the negative 6 meter. And if we wanted to see how many wavelengths that is, we can take the 1.2 times 10 to the negative 6 meter over the length of the wavelength, and we get that it is about 1.5 wavelengths. In part E, we're asked to find the momentum and minimum momentum uncertainty. The momentum is given by E over C, so that's 1.055 times 10 to the negative 34 joules second over the speed of light. And that gives us 8.28 times 10 to the negative 28 kilogram meter per second. And the uncertainty in the momentum is h bar over 2 times the uncertainty of the space, the length, as we done earlier. And this is oops, I made a mistake. My mistake was I plugged in the wrong value for E. The correct value for E, if you remember, was 2.48 times 10 to the negative 19th joule. Everything else should follow. H is the 1.055 times 10 to the negative 34 joules second over 2 times the uncertainty in the spatial length, which is 1.2 times 10 to the negative 6 meters. And that gives us an uncertainty of 4.4 times 10 to the negative 29 kilogram meters per second, which unsurprisingly is about 5.3% of the momentum. And lastly, for part F, we're asked for the appropriate number of photons per pulse. This is going to be an estimate, and if we take that each pulse has 2.00 times 10 to the negative 6 joules of energy, and we divide that by the total energy of 2.48 times 10 to the negative 19th joules per photon. That gives us an estimate of 8.06 times 10 to the 12th photons per pulse. And as we said, this would be a average, because we're just doing an estimate.